All right, welcome to 5B. So now that we've done increase, decrease, and max mins relative, we're going to start looking at um, absolute maxes and mins and higher derivatives. So the first thing before we do concavity, we're going to be looking at higher derivatives, which means more than the first. More often or not, you'll see second derivatives. But we can keep taking derivatives until we get to a derivative that's just zero. So when you're looking at a higher derivative, the second derivative is normally written with the two dashes instead of one. You'll also see d2y over dx2, or if you see it with just the regular d, it's going to be d squared sub x of the function. Now, the third derivative you can see written with the three dashes, but after the third, you're going to see it with that parentheses, and then your n is your number, which is going to be bigger than 4. So you got to be careful. If you see f with the parentheses to a power, that's a derivative. It's not a power of the derivative or a power of the function, like f squared or something. Parentheses means derivative. So we're going to take the second derivative of this polynomial. So first we find the first derivative. And then once we've found the first derivative, we're going to take the derivative a second time. So f prime is 20x cubed minus 12x squared plus 3. Now we're just going to take the derivative again. And we get 60x squared minus 24x. And you could see we could keep doing this until we get to 0. And the amount of times that you can take a derivative, you'll notice, is actually based on what is the highest power of the polynomial. Since my highest power here is 4, I can take this derivative 5 times. Because when I get to the fourth derivative, all that's going to be left is a constant. And then when I take the derivative again, it's just going to be 0. So kind of a fun fact. Now, I want to plug in 1 so that I can find the second derivative of 1, which means just plug 1 in to the second derivative, and we get 36. So the only difference is we're doing the derivative another time. So another example, we're going to find the second derivative for this function, but notice that we are going to need the chain rule. So we take derivative of the outside function, keep the inside the same. So you can see we're going to keep this x cubed plus 1 the same. That's my inside. And now I'm going to multiply by the derivative of the inside, which is 3x squared. Now simplify it all out first, and we get 6x squared times x cubed plus 3, or x cubed plus 1. Now we're going to take the derivative again. But now see, we don't need the chain rule. We just need the product rule. So here we have f prime g plus f g prime. So now we're going to simplify, multiply everything through, expand, and then we're going to consolidate terms. We get our final answer of 30x to the fourth plus 12x. So here's another one. We're going to find this second derivative, but now we don't need the chain rule, we just need the product rule. So take the first derivative using the product rule. F prime is just 1. So we get 1 times e to the x plus f, which is x. And e to the x is just its own derivative, so it just stays there. Now, notice when we take the second derivative, we still have a product rule, right? This is still going to need the product rule. This piece doesn't. So using the product rule again, you can see since this is the same as g of x, we're just repeating it. And we know e to the x is itself. So e to the x is special, so you got to be careful when you're doing those derivatives just to keep it straight. But it can work out kind of nice. And then simplifying, pulling out that e to the x. Now I have two multiplicative terms. When we're going to be doing the second derivative test, you're going to want to be able to pull everything out to multiplicative factors. It's just going to make life easier. Now, we're going to go again, second derivative, but this time I have a logarithmic function. And not only that, I need to use the quotient rule. So here we're going to use the quotient rule. And remember, the quotient rule is just the product rule with the subtraction all over g of x squared. Okay, so we have derivative of the top, f prime, which is 1 over x, times g, which is x. Now we're going to subtract, and I keep my f the same, ln of x, times my derivative of x, which is just 1. And now on the bottom, we have just our g of x squared, right? Because we're saying that this is our f of x all over our g of x when we're using our quotient rule. Now we simplify everything out, and we get 1 minus ln x over x squared. Now when I take the derivative a second time, again, I have a logarithmic equation and the quotient rule, right? But now my f of x is 1 minus ln x, and my g of x is x squared. So here we have g of x, which we keep the same, and we have our derivative of the top of our f of x. Derivative of 1 is just 0, but we have a minus a 1 over x now, right? Minus, keep the top the same, f is regular, times g prime, which is 2x, and then the whole thing goes over the g squared. And now g of x is x squared, so x squared squared. Now we're going to simplify. So this is just expanding those two multiplying pieces here. So we get negative x minus 2x plus 2x ln x. And then combining our like terms. And now we can actually get rid of one of those x's, right? I can pull one out because it's multiplying on both pieces. Now that only works because it's multiplying both pieces. It does not work if we're adding, okay? Just multiplying. So now we can pull that out, and I'm going to get negative 3 plus 2 ln x over x cubed. Cool. Now, remember how we did derivatives, and I was like, hey, guess what? Derivatives are awesome because it tells us velocity. Velocity is just speed, without the absolute value. Well, we can also find the second derivative of a position equation is the acceleration. That tells me, am I speeding up or speeding down, right? So am I going to be hitting the gas or am I letting off the gas, basically, is what's going on here. So now that we have this position equation that tells us about the distance of a car in feet at time t seconds, so feet per second, we can find out when is the car going forward or backward, and when is the car speeding up or slowing down. So the first question is pertaining to the velocity, right? Because if I'm going forward, my distance is increasing. If I'm going backwards, my distance is decreasing because I'm going backwards. So first thing we're going to do is find velocity, which is just that derivative. Now, once we found velocity, we need to figure out, here, we did both of them right away. So that's velocity. Acceleration is just that double prime, right? So I take the derivative again, I get acceleration. So the first question is velocity. Second question is acceleration. So that means that we need to find out when the velocity is 0. Because as you're driving down the road, when you're going forward, you're driving at a positive speed. But when I'm going to switch and go backwards, I have to hit 0 speed first, then go backwards. You can't just like flip-flop and it doesn't work, right? Everyone who's driven a car knows that you can't do that. You have to get to 0 at some point. So that's the point we need to find. Where are my critical values when velocity is 0? Okay. So set it equal to 0, factor out of 3, unfoil, and we've got at time 4 seconds or at negative 2 seconds, right? But we know that we can't do negative 2. So we can plug it in here and we can look. And we're going to plug in our stuff here and take a peek. Now I'm going to test everything, right? Just like we did before. So before determining whether or not something should be used, right? Because I said, hey, we can't have negative time. What I am going to say though is sometimes keeping everything the way it is and testing everything first, because sometimes there might be a trick that's coming along and you just haven't noticed it yet. So having all the information written out already before you put in your official answer can be beneficial. Now, not always. Sometimes it's just extra work. But just to cover your bases, it's not going to hurt you if you use all the information and then take what you need at the end. So we're doing our first part, right? I wrote up my number line. I have -2, I have 4. I pick some numbers in between each of the intervals. I pick easy ones, right? I'm always going to choose the first integer that's different unless I get 0 or 1. Zeros and ones are awesome. Otherwise, we're going to pick first integer. So here we have -3, 0, because I like 0, and 5. Now, plugging everything into our equation here, I'm going to get a positive, negative, negative, right? 3 is positive, -1, -7. So I'm going to get a positive number. There goes my arrow. Next, plug in 0. So now when I plug in 0, we can see here that I'm getting a negative number, right? So I have positive, positive, negative, positive, positive, negative. I get a negative number. Perfect. Now we're going to do it again. Now I'm plugging in 5 for the opposite side. So if I plug in 5, I'm going to get 3 positive numbers. So I have a positive slope there. So now that we have this information written out, we can say, okay, when is the car going forwards? When is the car backing up? So now we can say, okay, I don't really care about what happens before time is 0, because my car is not actually, driving. So this information we don't really need. But this information we do. Now, since my slope here is negative from 0 to 4 seconds, that tells me that we're actually backing up at this point. So from t equals 0 to t equals 4, the car is backing up, maybe backing out of a driveway, right? And then from t equals 4 onwards, the car is going to be going forwards. So that's the first answer to our question. We're going backwards from 0 to 4. And then we're going forwards from 4 on to infinity. So first question answered. Awesome. Second question, when is the car speeding up or slowing down? So that has to do with acceleration, right? Am I hitting the gas or am I letting off the gas? So we had our acceleration equation, and it gave us that it was equal to 1. For acceleration, it's 6t minus 6. So if I have 6t minus 6 equal to 0, we get t is equal to 1. So that's going to be our quote-unquote critical value for acceleration. So I put my 1 there. Now I'm going to pick 2 numbers to check. 0 and 2 are pretty good. I like those numbers. So plugging them into the second derivative, or the acceleration, first I get a negative number when position is 0. And then I get a positive number when my position is 2. So now this information tells me that we're actually going to be slowing down from 0 to 1. Now, that doesn't mean that we're not going anywhere, right? Because obviously velocity is not 0. But it does tell us that our acceleration is decreasing. So we're not speeding up, we're letting off of the gas a little bit, and we're slowing down. So that tells me that's where we're going to be slowing down. So second part of our question is from 0 to 1 second, our acceleration is slowing down. Okay, so the car is slowing down. And from 1 on, we're going to be speeding up. Okay. First taste of velocity acceleration. Kind of fun. So now that we've done a whole bunch of second derivatives, we are going to start doing concavity of a graph. Because we had a first derivative test, there is, of course, a second derivative test. And before we get to how to use it, we need to talk about concavity of a graph. Concavity means, is it concave up or concave down? And concave just means like it's curved, right? So it's like a cup. Am I holding water or am I spilling water? Is a way to think about it. Or cup or cap, whichever way you like better. So here we can see we're concave up here, and I'm concave down here. And here again is another one. We can see concave up is on the left side. Now concave down is on the right side. And again, we can see here we're concave down on the left, concave up on the right. And now another extra piece of information we have here is you can see that these red lines are the slope of the tangent line to the graph. And this slope here, as we're coming up to it, that's positive, right? So we're positive on the right, and then we switch and we kind of go negative slopes on the left. Hold on. Positive on the left, negative on the right. Mixing my lefts and rights. And here, concave upward, on the right, we are increasing on the right. So increase, 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 and in the center here, we're decreasing. Now, this spot that's been marked, this inflection point, that is the spot of the graph where at that moment, the graph is switching from decreasing its slope to increasing it. That kind of makes sense. This is the exact point where my graph switches from being concave down to concave up. That's the exact spot it switches. And that exact spot means that is the spot where my slope is now switching direction. In the same way where we found our critical values were when the slope went from positive to negative, meaning it hit 0. This is when our derivative of our slope is hitting 0. So that's telling us at the exact moment that we're switching from concave up to concave down. Here we can see this is a concave up graph, and it shows us that our negative slope here is on the left, positive slope is on the right, 0 is in the center. Another way we can see, hey, that's concave up. Here, we're still concave up, but you can see that the slope is increasing all the way through, right? We're always positive, but we are still concave up. So we can see this is a cup still. Here, we have positive on the left, 0, negative on the right. Here's our concave down. And here again, we can see it's continually decreasing slopes, right? We're not increasing anywhere, but it's still concave down. So here we go, left-hand side decrease, right-hand side increase, concave up. Here's another way to think about it as well, is when we have a graph that isn't quite what we'd normally think of as concave up, concave down. It's twisted sideways a little bit. But this blue section here is concave up, and this orange section is concave down. And here's another stranger case, one that we don't normally think of, but this is concave down, right? I can still pour some water in here and it'll hold. So we have decreasing on the left, increasing on the right. So now we're going to talk about how to test for concavity. So when we're testing for concavity, we have to have both the first derivative and the second derivative, and they have to exist on the function, on our interval. So there's concave up on AB if the second derivative is positive for all x in the interval. And it's concave down if it's negative, it's below 0 for all x in the interval. So another way to think about it is if you're happy, you got positivity, you're smiling. If you're full of negativity, you're frowning. It's a silly way to think concave up, concave down. So now we're going to find all intervals of this function where it's concave up or down and find all inflection points. Because remember that inflection point is where the first derivative is changing directions, all right? We're switching from decreasing to increasing or increasing to decreasing. And that tells us where our concavity flips. So first, take the first derivative. And then we need the second derivative, right? Because we're going to be looking for concavity. Now that we have that second derivative, factor it out into pieces. Because remember I told you we want it factored because it's going to be easier. One, you have to find your inflection points. Two, it's going to be easier when we're trying to figure out where our concavity is because we have multiplying factors. So now that we've factored everything out, we've got our 3 multiplying factors. We know where it's 0. It's going to be 0 at -3, at 0, and at +3. This is our concavity test, and it looks a lot like our first derivative test, right? But now I'm using inflection points, not critical. So I'm going to pick my numbers to test. So I picked -4, -1, 1, and 4. Nice symmetry there, easy numbers to plug in. So now that we've picked our numbers, we're going to do the same thing as last time. We're going to plug them back into the second derivative and figure things out. So here I've made up a chart. So this is one way that you can do testing for critical points and inflection points, if this works better for you. So I listed the x value here in the first column. And in the second column, I listed that second derivative with its multiplying factors. So now as I go down, what I'm doing is saying, okay, I plug -4 into 20 times x. Do I get a positive or negative number? I get a negative. -4 into x minus 3, I'm going to get a negative. -4 into x plus 3, I get a negative. Negative, 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 negative. And I did the same thing for each of the other ones, right? So now that I did all of that, now I have my negative, positive, negative, positive. So I know where I'm concave up and where I'm concave down. So now I just draw it in. I know that at -4, we're concave down, -1 concave up, 1 concave down, and 4 concave up. And that should make some sense here because this is a function to the 5th power. That's the highest power. So that lets us know that we're going to have 4 bumps inside there. It's always one less than the highest power of a polynomial. And we do. We have 4 bumps. We have 4 spots where we hit 0. We're going to have 4 concavities. So here's another. Here they came up with their own here. We have a inflection points we picked at 1 and 3 for this f of x. Here we've tested 0, 2, and 4, and it's come back second derivative positive, second derivative negative, second derivative positive. And that lets us know are we concave up, concave down, concave up, right? Here is a little bit of a tricky one. So here, the second derivative is 0 at x equals 1, but 1 f of 1 is not an inflection point, right? So if we find it here, 1 f of 1 is right here. Now, this is not an inflection point because I'm not switching concavity. So if I were to test this, if I were to write out a line and test my concavity on this, I'm going to put 1 as my inflection point. And if I tested it, it would tell me that I was concave up on the right and I was concave up on the left of it. So what it's telling me is that really I'm doing something like this, a big giant open concavity. I'm not switching from one to another. So kind of like how with our critical points, we said that it's not always a max or a min, that if we take a point and it's both on both sides the same, positive, positive, or negative, negative, it is not a max or a min. Same thing with concavity here. You cannot be an inflection point unless you switch concavity on either side. That is the legit definition. So it has to switch. So even though the second derivative is 0 at 1, it is not an inflection point because it does not switch concavity. So gotta be a little bit careful that we're double checking all of this. Oh, here, again, definition of an inflection point. Has an inflection point there, then the double derivative at that point is 0, or it fails to exist. Because we're allowing for that vertical slope, or we're allowing for that corner kind of a thing. We're allowing those things. We want to check them anyway, even though the second derivative doesn't exist there. We have to check it. So here we can see our concave down, concave up. And now we're relating it as well to our max and mins. So if I'm concave down, I'm going to have a max. And if I'm concave up, I'm going to have a min, right? Because that's just the definition of a max or a min. And I'm just relating it to concavity. So everything is interconnected with each other. So the second derivative test, full on definition of how we do it. We have to have a derivative, double derivative that exists on some open interval containing some x value c, and it exists on that interval except maybe not at c itself, because we're allowing for it to be undefined. And we want that the first derivative of that value is 0. Okay, so it's a critical value, right? And we're looking at how does that relate to our second derivative. So if the second derivative of that critical value is bigger than 0, then f of c is going to be a min, a relative min. If the second derivative of that critical value is less than 0, then it's going to be a relative max, because this second derivative bigger than 0 tells me that this is concave up. And if my second derivative is less than 0, it tells me it's concave down, right? And we know that at f0, f prime of c is 0, so we know that it's going to have a plateau here. And testing that plateau is going to tell us if it's concave up or concave down. And if the second derivative is 0 or it doesn't exist, then we have no information at all. We cannot tell anything. So that means you have to go backwards again and you have to check the first derivative test, right? So this is kind of a way of kind of skipping that first derivative test where we would draw the line and check all the intervals. Instead, you can just find what those critical values are and plug them straight into the second derivative, skip all of the testing of intervals, and just find out an answer. Cool? Okay, so we're going to do it. We're going to find all of the relative extrema of this function using our second derivative test. So first, find the derivative. So now that we found the derivative, we need to know where it's equal to 0. And it's equal to 0 at x equals 4 or at x equals -3, right? Just doing our factor out a -6 on FOIL. find an answer. So our second derivative here is negative 12x plus 6. Okay, I'm starting here. That's our first derivative. Second derivative is just going to be negative 12x plus 6. So now that I have that, I have my second derivative, I have my two critical values, I'm going to test them. I threw in the inflection point just because there it is. It's the purple one. That means that we may or may not change direction there, but we know the second derivative is 0 there. So now here's my chart. I have my x values, negative 3 and 4, that I'm going to be testing. I have my second derivative lined up there. Now I plug in my values. I got a positive and I have a negative. So I know that negative 3 is concave up, 4 is concave down. So we know negative 3 is a relative or local min, and 4 is a relative or local max. And because we're switching concavity, on negative 3 we're concave up, on 4 we're concave down, that means that 1/2 is an inflection point because it switches concavity. And then here's a graph of that. So here we have a function f of x. It's that fun polynomial here. And we've graphed on here, you can kind of see where our inflection point is and where our max and mins are. So here's the inflection point at negative 7/12. And here's a critical value, which is a local max. And then this is a local min. So just looking at it on the graph and determining it, we can see that information there. Again, looking on the graph here, we're given this function, 2x to the 5th minus 5x to the 4th plus 50. So here, now we have, this is a critical value, that's a critical value, critical points. And this point here, the 3/2, that's that inflection point. That's the moment where the function switches from increasing and decreasing. So my slope here has been getting smaller and smaller, right? But the rate of that change hits 0 here, and then it starts to increase again. I know it's kind of weird. So it's increasing its change on this side of it, and it's decreasing its change on that side of it. And that's why this is concave down and that is concave up. Now, this is also really helpful for looking at the point of diminishing returns. Because an inflection point is that spot where we're switching from increasing to decreasing, right? My slope has been increasing its rate, and now it's decreasing its rate. So that inflection point tells you the moment where your input output switches and starts to give less return. So see, you can see here that this is concave down. And that really means that the relationship between your input and output, you are not getting that benefit from the output from your input, right? So here, my output is increasing a lot, higher rate per my input. So I'm making a lot of money here. But as soon as I switch here at my inflection point, now my returns start to diminish. I start to be getting less for how much I'm putting in. So this is really your spot you want to watch. This is your sweet spot. And that's the benefit of using our concave up, concave down, our inflection points. Again, is giving us that sweet spot of where are we going to make the most money per how much we're actually putting in. Like we did with the bicycles, right? We figured the sweet spot of making the most profit. And here we're finding the sweet spot for our return on our money. All right, so done with concavity. So now that we've done concavity, we've done increasing, decreasing, local max min, we've done concavity. Now I can do absolute, which means absolute mins, absolute maxes. Like I cannot be any bigger, I cannot be any smaller. So we're looking at this graph here. We're looking for, do I have max and min? So we have some maxes and mins, right? x1, x2, x3, they're all extrema. I've got a max here at x1. I've got a min here at x2, and I've got another max here at x3. Absolute really just means absolute. Like nothing is bigger, nothing is smaller. Now, because this is an even function, both of my ends are going the same direction. Here, they're both going down. So as my function ranges over all values of x possible, I will not have a minimum value, right? Because both ends are still going towards negative infinity. There's not going to be any crazy change in them. They're going to go forever. So there is no min. There's a relative min at x2, but there is no absolute min. But because they both go down, both ends go towards negative infinity, that tells me I do have a max, right? There's going to be an absolute max. So now I'm going to look at my two maxes here. I've got x1 and x3, but x1 is bigger than x3. It's f of x1 is bigger. So that tells me that this f of x1, that spot is going to be my absolute max. These two here, x2 and x3, are still extrema. They're just local extrema or relative. They are not absolute. So here's our official definition of max, absolute max and min. So we have a function on some interval. C is a number in the interval. Then f of c is the absolute maximum of f on that interval if f of x is less than f of c for every x in the interval. Now this sounds a whole lot like our relative max and mins, but the difference here is that it's true for every single x on the interval, right? So it's absolute max on the interval itself. Before, we didn't require it to be absolutely bigger than everything else. I don't know if that quite makes sense. It'll make more sense when we go, and kind of how I showed earlier, right? How x1 was the absolute max, x3 was a max, but it wasn't the absolute max. And this is the same thing for absolute minimum, just flip-flopped. It's got to be smaller than everything else on that interval. So absolute extrema is there if C is either absolute min or absolute max. So same definition or same terminology, we're just throwing an absolute on there. So here we're looking at three different intervals, right? And it's showcasing absolute mins and absolute maxes. So here on number A, we have an absolute max at x1, absolute min at x2. We also have here at x3, this is still a max value, but it is not an absolute max. It's just a local max because it is bigger than this interval from x2 to x3. So it's bigger than everything on that interval, but it's not bigger than x1, right? F of x1. Here, absolute min, absolute max on B, it's a straight line, pretty self-explanatory there. On C, again, we have this where there are other mins and maxes, but they're not absolute. So here x5 is a min, and here x1 is a min, and x2 is a max. Here, I'll color code these things. And they have green for mins. All right, so we got a min here, we got a min here, but they're local mins. And then we have a local max here. So there's still mins and maxes, but they're just not the absolute ones because x4, f of x4 is a greater value than f of x2. And f of x3 is a lesser value than f of x1 or f of x5. So we still have locals and we have absolutes. We just need to distinguish between the two of them. Now, extreme value theorem tells us that if I have a function that is continuous on a closed interval, a to b, then the function must have an absolute max and an absolute min on the interval because it's closed. just like we saw here. These were closed intervals, and there had to be an absolute max and an absolute min. So here is another example of our absolute extrema. Here I have an interval a to b, and here we have an absolute min at x1, right? But there isn't an absolute max. As you can see, both of my ends are going towards infinity. This is another even function. Even functions have ends that go in the same direction, either up or down. Here we're going up. And since it's going up forever, even on that interval a to b, that means that there is no absolute max, just an absolute min. Now here we're looking at this interval, a to b, and here you can see that we have an absolute min, which is our a, but we don't really have an absolute max. It's a little weird. And this is because this function is not continuous, right? It's not continuous. I have a jump. That's not allowed. So I can get a min if I just shrink everything down. If I say a to x1 on the open interval, I get a min. And if I do x1 to b on a closed interval, then I would get a max and a min. But on this interval from a to b, x1 is neither a min nor a max because it is not continuous. So that's looking at the differences between continuity and not continuous, right? So now we're going to find absolute extrema. This is a little checklist on how to do it. So if we're going to find absolute extrema for a function that is continuous on a closed interval, first thing, we have to find all the critical numbers of f in AB. We're going to find that first derivative, find what x values make it 0. And then we're going to evaluate all of them. I want to find out what is the value of f in the actual function, right? And then I need to also check the endpoints of my interval because it's a closed interval. So I need to check the endpoints to see what is that function doing. Now, the largest value found in our evaluation steps, that's the absolute max. And the smallest value is going to be our absolute min. But if I'm finding absolute extrema for all values of x, so like if I had x squared, if I had e to the x, or something that's defined on all x values, then instead of considering the endpoints like we would do for a closed interval, we need to consider the end behavior of the graph. Like I had said a couple of times through these examples, hey, look, this is an even graph, so the ends go the same direction. Same thing here. So besides graphs that we kind of already know what they look like an exponential function or a logarithmic function, if we're looking at polynomial functions, if it's an even function, then both ends either go up or both ends go down. And they go up if it's a positive leading coefficient on our polynomial, and it goes down if it's a negative leading coefficient on the polynomial. If it's an odd function, we have one going up and one going down. And then it's the same on the other side. But if it's a positive leading term, then I've got down, up. And if it's a negative leading term, then it's up, down. You can kind of think of if you know x cubed is like this. Ooh, that's a horrible picture. We know then that, well, it's pointing down on the left and it's pointing up on the right. So that kind of a way to think about what does x cubed look like, what does x squared look like, just to kind of give you an idea of end behavior, because the ends are the same. It doesn't matter if it's x to the 68th. Still going to have two ends that go straight up or straight down. Okay. So here we're looking at just a table. So they've already figured out which candidates are allowed. So the x values that were allowed for extrema were -1, 0, 2, and 8. Plugging them into the function, we have -15, 0, -19.05, and 192. So these candidates mean that they're endpoints or they're critical values. And then evaluating them, the function gives us their values. And now I'm just going to pick what's the biggest number, what's the smallest number. Biggest is 192, smallest, -19.05. So that's our absolute min and max. Now the other two are nothing. We're not really classifying them at this point. All right, we're just looking for absolute mins and maxes. And here is the graph of that function that they use to make that table. So here we can see our absolute min and our absolute max, right? But we also have these other two numbers, -1 and 0. And we can see -1 was -15 and 0 was 0. So we know that this is actually a local min. This is a local max, which they've said here, relative min, relative max. But our absolute ones are going to be that 2 and 8. So now we're going to find the absolute extrema of this function on the interval 0 to 8. Now, unless they tell you find all extrema and label all of them, you just need to find absolute here. I don't want to know about local mins and maxes. I just want to know about absolutes. So first thing, like always, find the critical numbers, right? So we need the derivative, set it equal to 0 here. Simplify, factor that out. And so we have this fraction, 2 minus 5 over x to the 1/3. Now we're going to set it equal to 0. We're going to solve for x. Now this one is a little different because, as we can see, x to the 1/3, it's undefined when x is 0, right? We haven't done one of these yet where it's been undefined. So this is one where one of our critical values is undefined. So f prime of x is this 2 minus 5x over x to the 1/3. So notice that it's 0 at 2/5 because that makes our numerator 0 when x is 2/5. And that is inside the interval 0 to 8. So we're good. That's got to be a critical value. But remember how I said that the derivative is undefined when x is 0 because of this denominator? But 0 is defined in the function, and it is in our interval. So because it's defined in f, and it's in our interval, 0 is also a critical number. So this is where we need to include those undefined values. So now we have a critical value at 0, we have a critical value at 2/5, and then we need to check the endpoints. So we get our chart, we have 0, 2/5, and 8. That's the other endpoint we need to check. So we plug it into the function, and we get 0.977 and -84. And so you can see absolute min, absolute max, and then we don't care about 0 because it's in between. So not too bad. Here we're going to do it again, more absolute extrema. So first step, as always, we are going to find that derivative. Remember when I showed earlier, if it's not on a closed interval, it's open, then we have to consider the end behavior of the function, right? Because I'm not checking endpoints, I'm checking end behavior, what happens as the graph goes to infinity and negative infinity. So first step is always find the first derivative, find the critical values. And here we get 0, -4, and 1. So now we have our critical values. Now we're going to evaluate it at those values, right? So that's how we're going to figure out what our thing is, our chart. But when we're looking at those endpoints, right, instead of looking at the value of the endpoints, we're looking at end behavior, what happens as we go to infinity and negative infinity. Because f of x is a even function to the fourth power, it's going to have end behavior where it's going both up or both down. But it's negative, right? X to the fourth has a coefficient of -1. So both ends have to go down. So no matter what happens in the center of our graph, how many times it bumps or whatever happens, we know that at the end it's going to go down, both of them. And because both ends of the function on the graph go towards negative infinity, there is no absolute minimum, right? And we saw that on a couple. There was one earlier where it was like this, and I said because it's going, both ends are going to infinity, there can't be a maximum because it's just going to keep going. Same thing for this one. If both ends are going down, so there is no absolute min. So we don't need to consider any of the minimum values. I only need to consider the absolute maximum. So I check my critical values, -4, 0, and 1. And that gives me 148, 20, and 23. And then we just pick the biggest value, which is 148. So that's got to be our absolute max. So just making sure that we're checking our end behavior if I'm looking at all values of x, because those are really your end points, quotations around that. But we're just considering what happens as it goes to infinity. So likewise, if you think about it, if I have a odd function, let's say -x⁷ plus some other terms, then we're not going to have an absolute max or an absolute min, because one end is going towards infinity, one end is going towards negative infinity. There is no absolute max or min. So you're only going to have absolute max or an absolute min on the entire interval for any x if it's an even function. Now, I'm not talking about other functions, just polynomial. For polynomial functions, it has to be even. Fun tidbits. Okay, so now there's another theorem. It's called the critical point theorem. So suppose we have a function, it's continuous on an interval and some interval, and that function has exactly one critical number in that interval located at x equals c. So I pick an interval, and inside there we only have one critical number. If f has a relative maximum at that value, at that critical number, then this relative maximum has to be the absolute maximum of f on that interval. Same thing if it's a relative min, then that has to be the absolute min of f on that interval. Right, well, that's because we're picking an interval, right? I'm choosing some interval from A to B, just say. Okay, here's my C, it's in there. And we're requiring that f is continuous on that interval, and there's only one critical number, only one. So there's only one spot where the derivative is either 0 or undefined. So if there's only one spot, if I'm only taking this spot right here, then if this is a relative max, then that means it looks something like this. Since it's the only one there, it has to be the absolute max because it's the only one there. And it's the same thing for if it's the min. So again, if we have that a, b, some interval, there's my c. If that is a local min, and it is the only critical number on the interval, it has to be the absolute min because it's the only one there. I know, there's a theorem about it, kind of intuitive, but that's the theorem. So if it's the only one, it has to be the absolute. And so here, what we're going to be doing with these, this is like graphical optimization. So what we're saying is we're optimizing what is the greatest slope, right? So as I'm looking at this graph, here we're looking at the tangent, the lines with the greatest tangent to the curve, starting at 0 here, right? This is where we're looking. I'm looking from 0. I'm looking from 0 out. So here's 0 out to 80, all the way down. And this line here, from 0, right here, you can see that the line with the greatest slope is going to be tangent to the curve. So if I start out at 0, I'm going to draw a line. It's going to be the one tangent to the curve here. So that is my greatest slope. Now, the bonus of this greatest slope here means that this is going to be my point that we like the best. That's going to maximize here, optimize hours of labor and output. Kind of cool. All kinds of fun stuff we can do. All right, that's it for this week. Lectures are all up. Reminder again, exam 2 next week on Friday. I did extend the homework. It's due Thursday and Sunday this week because I've had issues with lectures getting up, and sorry about all of that. So I'm giving you guys an extra day since it's my fault for being a little bit late. If you have questions, let me know. I will probably put out another survey, see if anybody does want to do a review session for the next exam, because we have got through a lot of material, different kinds of differentiation. Now we're rolling into first and second derivative tests. Next week, we're going to roll into a little bit more complex differentiation. So it'll be nice to have a time for you guys to ask questions if you feel like you need it before the exam. So, all right. Have a good week otherwise.